I would like to spend a couple of words to really thank the organizers for this fantastic venue and the possibility to learn so many refreshing concepts and increase our skills. And I would like to introduce the topic that I'm dealing with right now with two good news. The first one, yes, we are going to share the slides, so don't worry, even if it's going to be dry, short, and academic, you're not going to lose anything because you're going to download the slides afterwards. And second, yes, the good news is going to be dry academic, and well, after the fantastic contribution given by Vitali, I suppose that my little talk is going to be very humble, so you will you will forgive me. So my name is Fabiano Spiga, and I am an independent researcher. I'm a data engineer, and I'm attending a PhD at the University of Tartu right now, and trying to survive the whole process. So what we're going to deal with today, it is going to be a sort of quick, broad-based panorama of all the libraries that Go offers us to relate with databases. And yeah, so let's jump into it. This is the table of contents, so the slides are 30 slides, and basically here I sort of listed the most interesting and useful packages that you can freely download from GitHub repositories, and then after we are going to briefly describe the main functionalities and features of each one of those. And after a brief description, I also added to the slides some code chunks and examples, so you will have all the right time on your own to go reading through the code and understand in details what they do, and eventually download the whole code base and start experimenting on your own on your computer. So I would like to start having two main concepts fixed, because sometimes, you know what, we get lost in details and we forget that the micro aspects of computer science, sometimes they weight more in terms of what you're supposed to do and how you're supposed to deal with them. And in particular, I want to consider two big things. When we code as software engineers, as developers, and we use programming languages, mostly our approach is procedural. So we have an imperative, procedural, and algorithmic thinking-based way to express code, where we describe the procedure from start. Then you have some kind of transformations or conditional statements that transform the thing that you are dealing with, and you have an output, okay? So you are describing and telling the computer, the compiler and the computer, do this in this sequence from A to Z, right? But when we are dealing, for example, with relational databases, okay, things get upside down. So when you deal with relational databases, always think that you have sort of a magic bottle. And you scrub the bottle, a genius pops up and says, you can express a wish, tell me what you need, and I will make it happen. Because this is exactly what happens with SQL. SQL means structured query language. And structured, it is the fundamental thing. Why structured? Because you always express and describe the output you wish, the output you wish from the system. And how you do that? You say select from where, group by, order by. So this sequence is fixed. It is the way the database engine thinks and is structured in itself. So you are describing your wish. I wish the output to be like that. And through these 5 statements, select, from, where, group by, order by,
you describe the output, and the engine is automatically producing it and optimizing it by itself, like if it was the genius of the bottle, right? Now, the problems arise when you have to mix the things together, and you have to sort of hybridize two beasts that are one the opposite of the other. So, given this sort of precondition, now we are looking at ORM versus Vanilla SQL. So what the purpose of ORM? ORM means Object Relational Mapping, okay? And as Wikipedia describes the thing to us, ORM allows accessing relational databases in the form of abstract objects. So you're creating some sort of object that are supposed to facilitate some procedure. ORM, it is good for prototyping and for CRUD operations, so it's create, read, update, and delete. But it is, usually it is annoying and cumbersome for long-term maintenance due to the need for more complex queries. And then Go offers SQL-related management packages. We will see some of them. And it still requires pseudo SQL DSL, which means domain-specific language, okay, which means to reinvent SQL in a set of Go function calls. It's because basically, when we're using SQL through Go, we are nesting and wrapping SQL queries, but in a formal syntactical way that Go can process and compile. And so this DSL queries and manual mapping via query text and struct tags that, if incorrect, would fail at runtime. Now, I repeat this thing. This is very important because it's a good practice to approach coding trying to catch all of the bugs and the weak spots of your code at compile time, because if you're going to find yourself with runtime bugs, it's much, much harder to find a solution and understand why the system is not behaving the way it is supposed to do, right? So, let's go further. This is a sort of depiction of how an ORM is structured. So on the bottom you have a data access layer, which is basically made by a data mapper and an active record. And on top you have a database abstraction layer, which is the querying language of choice, right? So this is the simple abstract depiction of the whole thing. Let's start with the first package. It's called GORM. It's the GORM Library. And the main features that we are going to see, so of course, these are the links to the website, the repo, and I'm not going to open them right now. It is extremely simple to install the package through the command line, so it is the usual go get something in Go, and that's the way to have it on your computer. And so just a quick panorama of the main features that the GORM library offers. You can have associations, you can have hooks, eager loading of your data, transactions, context, batch, SQL builder, composite primary keys, auto migrations, logger, extendable flexible plugin API, and tested. So these are all the main features that you can perform through this formal function calls, okay, and these methods. I'm not going to bother reading every single one of them. Just for your information, go through the slides and eventually launch the application and have a creative experimental approach. And so here as well, I have written down the most self-evident examples in terms of codes. I'm not going to read through the code itself, but okay, for example, here you have a simple implementation in Golang for GORM. And so you have you import the packages, you declare a struct, and then if you immediately go through a main testing chunk of code, you are using GORM function calls to operate over the data and produce some transformations with an output, okay? So you can manage the schema with the data, and of course, another thing to remember, when we are dealing with relational databases, the main abstract architectural feature, you have data schema implemented, okay? So it is exactly the opposite of NoSQL languages. NoSQL databases are unstructured, so they are much more flexible. But on the other hand, when you want exactness and univocal references through the use of primary keys and foreign keys and tables, so relational database guarantee the best in terms of correctness of the output that you are calling. And again, so you can achieve and perform read queries, update queries, updating multiple fields at once, and delete something from your database through this GORM-based function calls. The second one is called Squirrel, and it's a fluent SQL generator for Go. So what it does, it avoids some SQL query writing issues and does not explicitly support tuples, but you can get some turnaround solutions, okay? And again, here I simply collected some basic code example, for example, building SQL queries from composable parts. And so you are nesting the SQL query in a variable, and you can call squirrel-based function calls to operate some transformations. And the example number 2, you can build SQL queries from composable parts again, and there is a different alternative way to achieve that, but the concept is the same. And you can execute queries directly, and you have also the possibility to perform conditional query building. And of course, you can directly interact with the cache, and so make caching and related statements. So this is it. You can go and check the examples by themselves. And of course, I didn't tell you, but every code chunk that I am using as example are by conventions highlighted by different colors. So in red you have always the keyword, in green the string. The highlights of the code are in this light orange color. The comment is in light gray, and in black color the code. Okay, and this is consistent throughout the whole presentation of the code chunks. So Squirrel here is shown how to create interaction with PostgreSQL. And for example, you use question marks for placeholders, and Squirrel replaces them using a placeholder format. And for example, here we have an example on how you can retrieve an ID from the database. And the last example, you can use escape question marks, which are made of double question marks. And double question marks generate the equivalent of $1 placeholder. So these are sort of syntactic sugar to control your data flow, okay? And then another interesting package is called Structable. And it is a Golang struct to table database mapper. So, and basically what it does, it maps a struct record to a database table via a structable recorder. Structable intended to be used as a backend tool for building systems like active record mappers. It works by mapping a struct to columns in a database, and it satisfied a CRUD-centered record management system through a standard contract. And as usual, you use this command line interface call to install the whole code base from the repository. And here again, as a quick start, we have some simple examples. So here, structurable standard contract to be filled. Basically, what you do, you instantiate a new type. This is an interface, and basically, through standard calls, you are describing exactly what your code is dealing with. So you have, for example, bind, interface, insert, update, delete, exists, exists where, load, and load where. So through this structured and fixed function calls, you are describing, on the other hand, the things that were briefly listed up above, okay? And now, the next one is called DBX. And by the way, and I just want to tell a curious sort of glitch that happened by mistake, because when Egon was asking me to present this package, that, by the way, it is maintained and designed and developed by Storage, which is the company that Egon is working with. So I discovered that there is an identically named DBX package on GitHub. So basically, I completely skipped this thing. I described the other package, and when I gave the draft to Egon, I said, "Okay, guy, I mean, it seems nicely done, but it is not what I was thinking about." So there are two packages that share the same name, and we are going to see both of them. So DBX is a database schemata and code to operate with it. It generates database schemata and code for database manipulation. It takes a description of models and operations to perform on them, and it generates code to interact with SQL databases. So it generates code for all the models and fields and uses the Postgres SQL dialect, which is called PL/PG SQL, which is a procedural language, okay? And there is the link to the actual manual from Postgres website. Nevertheless, DBX is designed to be agnostic to many different database engines. In fact, you can, it is ready-made to be interfacing itself with PostgreSQL and with SQLite 3, all right? And the grammar DBX file has two constructs, which are tuples and lists. A list contains comma-separated tuples, and tuples contain white space-separated strings or more lists. And here are the examples. For example, here we have the way to declare a simple model and place it in a .dbx file. So this is the extension of the file. It's called DBX. And then you build the source via command line. So you have a DBX as first invocation syntactic name, and then Golang, and then the name of the file. In this case was a simple example.dbx. And the former produces an example Go file within the same directory. So it parses the code described from DBX, and it transforms it in a proper .golang file, okay? So, for example, here you can generate a schema using the command line. So you have DBX schema, and then you use the same file created before, example.dbx, and produces a file example.dbx.postgres.sql with SQL statements to create the tables for the models using the above-mentioned procedural language dialect from PostgreSQL. And here is another example. You are creating schemata from both PostgreSQL and SQLite 3, and you see the invocation is exactly the same. The only thing that changes is that, wait a second, yep. So basically, you are using DBX schema for the first invocation, and then you are using the specification Postgres and SQLite 3. And the second is DBX Golang. So basically, you are creating two different examples matching both Postgres and SQLite 3 specifications at once, all right? And the former produces the appropriate schema according to the specific SQL dialect specified by the command line flag /d and /dialect. And these commands are intended to normally be used with /go colon generate directives. So the methods interface is shared between the TX and DB interfaces and will contain methods to interact with the database when they get generated. So here is the way to instantiate a struct definition, all right? And then you can instantiate concrete type DB and TX and their related interfaces, and here are the methods. So this is the way that DBX wants them expressed and written down. There are 4 kinds of operations, which are the classic basic create, read, update, and delete, and this is the way how to do that in DBX. So you can add one of each operation for the user model based on the primary key, and here is an example how to do that. So you create, update, delete, and read, and the way you express them through the proper syntax. And you can regenerate the Go code to expand database interfaces. So here are the interface invocation, and so you can create a user, delete the user by primary key, get the user by primary key, and update the user by primary key. So the primary key is always our main hook. And finally, you have the DBX exposes transactions handling, but it can be verbose in commits and rollbacks. So if so, define a package as a collection of multiple files. For example, a helper method is another file to the pointer DB type, okay? So create user can be succinctly written as, and this is the way to express in a very dry form the create user instantiation, and the function as an added helper method in a separate file, it gets described in this way. So these are simple examples on how to achieve those functionalities. Next one, PGX. So it is a PostgreSQL and Cockroach DB driver and toolkit. So it is used to perform native direct SQL queries, but it is easy to make typos, so be careful how you express the syntax. It enables PostgreSQL specific features that the standard database SQL package from Go does not allow for. And it is excellent because it has a lot of flexibility and performance comparing to database /SQL. And for example, it can use PostgreSQL specific types. Types such as arrays can be parsed much quicker because PGX uses the binary format. So you don't have parsing, coding and decoding phases. Everything is directly managed in binary format. Then you have automatic statement preparations and caching. So PGX will prepare the cache statements by default, and this provides a significant free improvement to code that does not explicitly use prepare statements. And with certain workloads, it can perform nearly 3 times the number of queries per second. So you have an improvement in performance of 3 per, which is rather interesting. And then you can perform batched queries. So multiple queries can be batched together. Instead of expressing each single query by itself one after the other, you create a batch of query and you launch them at once, and you minimize the network round trips. So you just have a network call, you push through the network only once, and there is a whole list of queries that gets performed. And toolkit components, you have underlying packages can be used to implement alternative drivers, proxies, load balancers, logical replication clients, etc., etc. So it is a rather wide collection of options that you can with which you can customize your code and optimize your code. So here again, this is the main list of PGX family libraries. I won't go through reading through them. It's simple. I mean, There is a huge list of things that by default can be leveraged to obtain and optimize the specific functionalities that you want to invoke through Golang and the database of your choice. And this is the final part of the list. So I kindly invite you to go check them out and possibly spend some couple of hours making experiments and launching these functionalities by your own. And again, as a quick start, I collected some simple examples. So here again, you have, for example, here you are dealing with a URL example. You are using Postgres as a specified target reference with the username, the password, and the localhost, the port number, and the database name. So this is the way to target specifically your database hook. And here there are all the previous transformations and family libraries that you are invoking with this code examples. And then we have SQL LC, and it compiles SQL queries to type safe go. So you basically, what you do here, you write Vanilla SQL code, which is standard SQL code. You run SQL LC to generate code with type-safe interfaces to those queries, and you write application code that calls the generated code. Okay, so this is the sort of transformation steps to achieve what you will through SQL LC. It produces type-safe code from the SQL source, and it maintains runtime performance, but it can introduce code generation and extra tooling. The input-output SQL mappings from the starter database and SQL package are straightforward, but they do not scale. And it's trivial to make mistakes on mappings that are not caught until runtime. Big warning sign. Remember, our main worry should be to catch all the possible non-performant, non-optimized behaviors and glitches at compile time, and skip as much as possible the problems that are gathering at runtime, because it's much more difficult to find and optimize when it is basically too late. And then it is wise to avoid using struct tags, handwritten mapper functions, unnecessary reflection, unsafe empty interfaces, or add any new dependencies to your code. So this is a list of suggested good practices to avoid getting in trouble. And yes, it's over. And here we have another chunk of examples. And so, last one, the second DBX. It means that you can enable full table data key value caching. This is a unique feature because basically the possibility to read key value cached full table data, it allows you to deal with huge amount of data. I mean, we are talking about terabytes or even petabytes of data. So this construct makes you manage those effortlessly, all right? And it interfaces with SQLite 3 by default. And just to understand, so when your query is directly performed on SQLite 3, you get a 3 per sort of performance optimization per second. And when dealing with caching, comparing to Redis, you get a 350 times more performant queries comparing to Redis, of course, given the same amount of data that you are fetching. And this is it. So you can perform nesting of structures. It supports reflections, and it supports MySQL and SQLite 3 and memcached databases out of the box. And here you have just simple chunks of codes, and basically this is it. So this is the panorama of the most interesting and useful packages for Go and database interfacing and data management. And that's it. Thank you very much.